So this week is all about solution chemistry, and solution chemistry actually happens to be one of the harder units in the course, but we are going to simplify it as best we can and go through really the highlights of what you need to know. So if you go back to the first quarter of the year when we learned about the different phases of matter, you remember we actually talked about solutions then. And what solutions are homogeneous mixtures. In other words, they're mixtures of two or more pure substances that look the exact same throughout. So no matter what portion of a solution you look at, it's always going to look the same. The other thing about a solution is that because it is a mixture, there is no set composition. In other words, if I'm making Kool-Aid, I can make the Kool-Aid very strong, or I can make the Kool-Aid very weak. So here's my glass, and here's my other glass. In one glass, I'm going to have very strong, very bright red Kool-Aid, and in the other glass, I'm going to have kind of a lighter red Kool-Aid, which is a little bit weaker. And we say that the solution that has very strong Kool-Aid, we say, and I got the wrong pen, but we say this is concentrated. And we say that the solution that is very, very weak, or doesn't have a lot of Kool-Aid in it, we say that's dilute. But they both look the same throughout. They're both homogeneous mixtures, and they're both solutions. Of course, the other thing you're probably familiar with is the parts of a solution. And the parts of the solution are the solute, and the solute is what is being dissolved. The solvent is what does the dissolving. So in our Kool-Aid example, the water is the solvent, I should say dissolving, and the Kool-Aid powder is the solute, and then together they make the solution. And this process of dissolving a solute in the solvent is called solvation. And whether or not a solute can actually dissolve in the solvent is determined by the intermolecular forces of the solute and the solvent. Really, we have this idea in chemistry of like dissolves like. So like things dissolve other like things. For example, salt is ionic and water is polar, and so because they both have the charge, they'll dissolve with each other. Oil is nonpolar and water is polar, so that's why oil and water don't mix. It's this idea of like dissolves like. And there's more information in the written notes on both the process of solvation and this idea of like dissolves like. So there are actually a lot of types of solutions. I know we normally think of solutions as solid substances like Kool-Aid powder dissolved in liquids like water. But we have solutions that could be mixtures of two gases. For example, air is a homogeneous solution of nitrogen gas and oxygen gas and carbon dioxide and water vapor and argon and a bunch of other other gases. You've also seen, for example, if you ever drink carbonated water, that's a gas dissolved in a liquid solution. But the most common kind of solution, the most important kind of solution we see in chemistry is that it's called an aqueous solution. And this is normally referred to as a solid. And I put the word ionic in kind of green so you see it, but it's got to be an ionic solid. And when you dissolve an ionic solid in a water solution where water is a solvent, it's an aqueous solution. And it's important in chemistry because we can do a lot with it, and they're relatively easy to make. So because we make solutions all the time in chemistry, one of the things that we want to know is this idea of concentration of solutions. And concentration is a measure of how much solute is dissolved in the solution. If a solution is very, very concentrated, so we say it's concentrated, it's got a lot of solute. You ever hear of buying concentrated orange juice? What they've done is they've actually taken the water out of the orange juice so that you can package it in a smaller packaging. You buy it at the grocery store, you take it back home, and you add water to it to make orange juice again. But it was a way, really popular probably back in the 70s and 80s before you were born, to prepackage and sell orange juice on the cheap. So that's concentrated. They also use this with concentrated soups and a bunch of other things. If there's not a lot of solute, we say that the solution is dilute. So there's not a lot of solute. And sometimes you'll, see people spit out their coffee because their coffee is weak. It's because there's not a lot of coffee in that water. That's a very dilute solution. A lot of times dilute solutions are very important. For example, when we're trying to put intravenous fluids back into the body, we don't want that to be full of the salt and electrolytes because you could actually kill a person. So you really want this to be the right concentration. So to make sure our concentration is right, we have a unit that measures the concentration or measures how much solute is in the solution. And that unit is the big capital M, and that stands for something called molarity. And we measure the concentration of solutions in molarity. Molarity is equal to the moles of solute. So remember, this is all about how much solute is in there, divided by, and this is really key, it's liters of solution. So how much solution we have in liters. What you'll find in a lot of chemistry problems, because we often use smaller amounts, is that the measurement of how much solution you have is sometimes in milliliters. So you'll always have to convert the volume to liters in order to solve these problems. But molarity, which is a measure of concentration, is moles of solute per liters of solution. And we say that the concentration is either molar, or we say the concentration is molar. So like, let's say like I have a 1 molar solution of sodium chloride. That means I have 1 mole of sodium chloride dissolved in a liter. Usually they're aqueous solutions, usually it's water. So the best way to get used to this weird unit of molarity is to do some practice problems. So let's just do a couple, and you'll see that it's not terribly difficult. So this problem says, what is the concentration? And remember that concentration is molarity of 5.00 liters of an aqueous solution that was made with 2.50 moles of sodium chloride. So we're asking for concentration, and concentration is this big M, it is molarity. And remember, that's moles of solute over liters of solution. So let's look at our problem and see if we can figure out the solute. And I'll put the solute in blue. We know that this is an aqueous solution, so the solvent is going to be water. And since it's a sodium chloride solution, sodium chloride is the solute. Therefore, we have 2.50 moles of sodium chloride. And then we just have to find the volume of solution. In this case, it tells it to us. We have 5.00 liters. It's already in liters, so there's nothing special to do. So we say 5.00 liters of solution. And then we solve it, it's 2.5 over 5, or 0.500 molar sodium chloride. And we write our NaCl right there. So there's your answer. Sometimes, actually a lot of the time, you'll actually see concentration expressed by putting brackets around what the main solute is. So this is often written with a bracket here, NaCl, and what this means is concentration of sodium chloride. So the concentration of the sodium chloride solution is 0.500 molar sodium chloride. So this is practice problem 2. It says a beaker contains 10.0 liters of a 6.0 molar sodium hydroxide solution. How many moles of sodium hydroxide are in the solution? We'll go back to our original equation, and we'll remember that concentration is equal to moles per liter. That's moles of solute. In this case, though, we're not trying to solve for concentration. We're trying to solve for this moles. So we'll have to rearrange our equation. And the way we do this is we say that moles of solute is equal to the molarity, or the concentration, times the volume. In this case, we have 6.0 molar solution times 10.0 liters. Remember though, this has to be in liters. And obviously 6 times 10 gives us an answer of 60 moles of sodium hydroxide. That's NaOH. The 60 point, for those of you who are wondering, this is 2 sig fig. And so to make sure this was 60 with 2 sig fig, I just put the decimal point right there. That's a sig fig thing, so we don't forget that. So this last one is going to take us the third way, which says, what is the volume of a 0.250 molar potassium iodide solution that was made with 2.000 moles of potassium iodide solute? So once again, remember that molarity is equal to moles over liters. This time, though, we're trying to find volume, so we're going to find that volume in liters. When you solve this out, it ends up being moles times liters. Molarity times moles equals moles. and then you resolve it so the volume is equal to the moles of solute over the molarity. In this case, we have 2.000 moles of potassium iodide, and the molarity we told you was 0.250 molar. And when you solve it out, you get, with 3 sig fig, 8.00 liters. So we have 8.00 liters of potassium iodide solution. So the good thing is, knowing this, we can make a solution of pretty much any concentration we want in the laboratory. So let me give you an example. Let me show you kind of wherein the problem lies. So this question says, how do you make 100 milliliters of 2.00 molar sodium chloride solution? So obviously this is going to be a solution of salt and water, but you're in the lab. So the question is, you've got to figure out how much salt you're going to add to the solution. So in this case, you're going to want to solve for moles. Since we're given the molarity and we're given the volume, we know that if molarity is moles over liters, then moles is equal to molarity times the liters of solution. In this case, though, we don't have liters, we have milliliters, so we have to be very careful. We're going to say it's 2.00 molar times, and this is 0.100 liters. You gotta be able to do that kind of in your head pretty quick. And when that comes out, that's gonna give us 0.200 moles of sodium chloride. And at this point, you're probably going to be stuck. The reason being is we can't, off the top of our heads, go out and measure 2.2 moles of sodium chloride. But what we can do is we can measure all of this in grams. So we have to use our stoichiometry and go to step 2, which is we have to take our 0.200 moles of sodium chloride and we have to multiply it by the molar mass. So in this case, we're getting rid of moles of NaCl and converting it to grams of NaCl. And using our periodic table, it's 58.4425. And when I solve this, I get 11.7 grams of NaCl, and that is a number I can work with. So we're going to rewrite this at the top. I'm going to erase all of this. And let's talk about making that solution. So the first thing we're going to do is we're going to weigh out 11.7 grams of NaCl. And that's easy. We're going to weigh it out. And then we're going to put it into this really cool device called a volumetric flask. And it's a very tall, long-necked flask that it's got a ring right here. And there's one for each size. And this ring would be exactly at 100 milliliters. So what we're going to do is we are going to make it exactly 100 milliliters, but we're going to put the salt in first. And there's a reason why. So there's our salt that we weighed out. It's 11.7 grams. Finally, the very last step is we're going to fill it with distilled water. So we're going to fill it with distilled water all the way up to this ring. So we have exactly 100 milliliters. We're going to swirl, we're going to shake, and then we have it there. Our solution is done. If we had added the water first and then the 11.7 grams of salt, that wouldn't work because what happens is salt contains volume. So if I add the water first and then put the salt in, it's actually going to rise above 100 milliliters and we wouldn't have 100 milliliters solution. So it's really, really important that you put your solute in first and then fill the rest of the way to solvent. Obviously, there's some other considerations here, and if we had a lot more time this year, I'd talk about it. But one of those considerations would be, what if I don't have a 100 milliliter volumetric flask? Well, you'd have to make the same concentration of solution, but in a larger quantity, and then you'd have to pour it into a graduated cylinder to measure the amount you want. So there's a lot of ways to do this, but right now, this is the way you do it. Measure out the mass of what you need, put it into the flask, and then add the water. So the last little bit of the notes that you can read through are on this idea of solutions and solubility. We've talked a lot about dissolving salt or dissolving these solutes in water. But what we haven't talked about is what if you can't dissolve any more solute in a solvent? And we've all done this. So let's say you're making Kool-Aid, and I've got this Kool-Aid glass right here. So there's my glass of Kool-Aid, and it's going to be nice and full. but I've added too much powder to my glass and it can't all dissolve. So what you actually end up happening is you have a little bit of this red powder that's sitting on the bottom that won't mix in. We say in this situation that this solution is saturated. And you've probably heard this term before. I usually talk about like the ground is saturated when it rains a lot. Saturated means it can hold no more solvent or no more solute. You've dissolved the maximum amount of solute that you possibly can. You could also have a solution that doesn't have the maximum amount of solute, and that solution we call unsaturated. So this would be just a regular glass of Kool-Aid. It could probably hold some more. We say it's wrong color. We say it's unsaturated. In an unsaturated solution, it can hold more solute. And then there's one more really unusual one that you actually experience all the time. If you've ever drank sweet tea, or you ever drank a beverage that was super, super sweet, maybe it's a very, very bright red Kool-Aid, we say this solution is what we call, and it's one word, but I might have to write it as two. We say this is super saturated. And what it means for the super saturated is it's actually holding, it's not can hold, it's holding more solute than it should. So it turns out that solubility, or how much solute a solvent can hold, is dependent on a lot of things, but one of them is temperature. Hotter solutions or hotter solvents can actually hold more solute than colder solvents. So if you ever make sweet tea, what they do is they boil the tea and add the sugar, because that way more sugar can dissolve in the tea at a hot temperature than it is at a cold temperature. And you've seen this before if you've ever worked in a kitchen. So hot liquids can hold more solute. And then the solute stays dissolved when you cool the solution back down. So that's a super saturated solution. So that's a really, really brief introduction to our distance learning on solutions. Obviously, there's more we're going to cover this week. We're going to very, very, very briefly touch on acids and bases. What are your expectations for the week? Obviously, that you viewed this video and that you read through the notes. There's a problem set and then a place to submit your answers in quiz format. I'm really looking to see just that you try and that you've understood it. If you don't understand, it's not the end of the world. I do provide you an answer key once you make a submission so you can go over it. And we also have class twice this week from 12:10 to 12:40 where you can ask me questions on Monday and Wednesday. Or if you just want to email me and ask me questions, that's fine. There are two things you need to turn in to pass. So remember, you have to earn your pass every week. The two things to pass this week are actually very similar to last week. Thing number one is the quiz of answers. So you do the problem set and you just put your answers in the quiz. That should be relatively easy. And the second thing is there's a gizmo on pH analysis. It's actually a really, really easy gizmo. So just do the worksheet that goes with that. It's very simple. Those are the two things you're expected to do this week. You do both those things, you try, you do a decent job, you get your pass, and we just keep moving on. Additionally, there's also an extension activity. If you still don't like your Q3 grade, you can do the extension activity. This week's is easier than the previous week's, and you don't need as many materials for it. So if you try the extension activity, you do a good job, I will consider raising your third quarter grade a little higher than, your semester grade a little higher than your third quarter grade. As always, I will see you on Monday and Wednesday at about 12:10.